in this case is you look at the total number of successes or non-defects in the N trials. If I say a head is a success, I flip a coin 10 times, I'm going to be interested in how many heads I get out of those 10 flips as an example. So definition of random variable, well, we'll call it Y. So that's one is a general characteristic. So if random variable Y reflects the total number of successes in N independent identical trials that have constant probability P of success and 1 minus P of failure, then Y has something called a binomial probability distribution function defined by the probability of Y, the number of successes, for a particular value of little y, is equal to N choose Y, P to the Y, times 1 minus P, N to the Y. And Y is going from 0, 1, 2, 3, all the way up to N. The mean of the binomial distribution, E of Y, is equal to N times P. The variance of this distribution is equal to N times P times 1 minus P. So again, what you could envision, this is where lots of things come into play. Go back to what is independence. You're able to use the product of the probabilities to determine whether you're going to have. Now in this case we're looking for, so imagine the 10 flips of the coin, and there's some examples we're going to go through. 10 flips of the coin, I'm interested in knowing probability that I have 0 heads, probability that I have 1 head, probability that I have 2 heads, 3 heads, all the way, what's the probability that I have 10 heads in 10 flips of a coin? N would be 10, and what's varying is 0 heads, 1 head, 2 head, 3 head, 4 head as the N choose Y. So let's go through an example of this. And again, in class we'll go through a number of these to make sure you kind of get the concept here. So it is claimed that 15% of ducks in a particular region have, I'm terrible at my pronunciation, patent scytosome infection. I have said this every semester. I always get it wrong. Infection. So suppose that 7 ducks are selected at random. Let X equal the number of ducks that are infected. So 7 ducks selected. You assume that there's like this huge number of ducks. So it's independent. Your trials of drawing a duck. 15% are infected. It is claimed. So what we're going to do is look at what's the probability that 1 duck is infected out of the 7. Well, that is equal to 7 ducks picked, probability that any one of them is infected. What's the probability that that one is infected? 0.15 to the first power. What's the probability that 6 of them are infected? That's going to be 1 minus 0.15 or 0.85 to the 6th power. So you have that product going there. You have 1 success, 0.15, times 0.85 to the 6th power. What does that turn out to be? If you work out, you've got a 0.396 probability that 1 duck in 7 would be infected. What's the probability that at least 2 ducks are infected? Well, you could go through the effort of saying that's the probability of 2 plus probability of 3 plus the probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 7 ducks. You could add up all those different probabilities. First, calculate each one of those. Or, we know again from our probability basics that the complement of the entire sample space, the probabilities are going to add up to 1. If we want probability at least 2 ducks, then we could say that's equal to 1 minus the probability of 0 ducks or the probability of 1 duck is infected. And so 1 minus, you see the term, the 7 choose 0. That means 0 ducks are infected. That has a 0.15 to the 0 power times 0.85 to the 7th power. That gives you this piece right here, the 1 minus 7 choose 0 times 0.85 to the 7th power. That's minus P of 0. And then minus the 0.396, which we had figured out in the first part of this problem. And so that's a probability of 0.28 that at least 2 ducks are infected. And that's, you would guess, let's see, so there's probably a 0.15 that a duck is infected. Fairly low chance of that. So probably at least 2 ducks infected. Fairly low chance of that out of 7. So alternatively, you can look up in your table A1 in your textbook. You'll see the actual probabilities given to you for each one of these instead of going through these formulas and figuring it out. Here I've just given a few. Some of these are fairly old examples, but it gives you a flavor of some of the other where binomial distribution or variance of it actually was identified as the best fit for different problems that arose. Got a textbook exercise for you to work through. Go ahead and check your course outline to see which example exercises I've mapped to this, just as practice. Okay, so that's a brief look at the binomial. Moving on to something called the geometric distribution. Okay, so we looked binomial, repeats Bernoulli trials. 10 Bernoulli trials over and over. What's the total number of successes in those 10 trials? Here at the geometric, we're going to look at the same kind of structure, repeat identical independent Bernoulli trials until the first success occurs. So you keep going until you have that first success. You include that as your number of trials you need to do. So what's the probability? So if I have that constant, so back to the duck example, 0.15 probability that any one duck was infected. How many times, what's the probability that I have to check 3 ducks in order to have my first success, my first infected duck? What's the probability I had to check 10 ducks before I got my first duck that was infected? Kind of a hard thing to say. Okay, so in geometric, that's the, and this is the big difference between these different distributions. What is the question that you're asking? And thereby, what is the random variable that you're going to structure to say, okay, in a binomial distribution, you're asking the question of what's the probability of this many successes in this many trials? In this case, we're saying how many trials do we have to have until we have our first success? So that's one way to remember these different distributions. Remember the question that they address. Okay, so definition. Random variable y reflects the total number of independent, identical Bernoulli trials until and including the first success. Then y has a geometric probability distribution function defined by P of y is equal to, so here's your one success, and then for the y minus 1 trials, you had failures. So back to back, 1 minus p, 1 minus p, 1 minus p, right? So you had, and y, therefore, could go on and on and on, right? If you assume an infinite population of infected ducks, you could have, what's the probability? You would have a probability saying, well, what's the probability that I had to check 99 ducks, and on the 100th duck, I ended up with my first infected one? What's the probability that I had to check 1,000 ducks? The first 999 were not infected, and finally on the 1,000th duck, it was infected. My first one was infected. So that is why you have y going from 1 onward. The mean of this distribution is equal to 1 over p. The variance of a geometric distribution is 1 minus p divided by p squared. Again, different probability and stats course would have you prove these. And I don't actually remember if in your textbook you see the proof, but it could be, could each of these be proven by the definition of what is an expected value that was provided previously. Okay, class example. Geology study indicates that an exploratory oil well drilled in a certain region should strike oil with probability 0.2. That's your probability of success, 0.2, strike oil. What is the probability that the first strike of oil comes on the third well drilled? So let x is equal to the number of the well on which oil was first struck. Then x has a geometric distribution with parameter 0.2. So probability that you had to drill go after three different oil wells would be 1 minus P to the second power. So you had two failures, and then finally you had your first success. So 1 minus P squared times P, and that turns out to be the 0.128. Again, some additional examples of geometric where, and these, I believe these were actually published papers, and where people said, hey, this is my problem. This sounds like a geometric distribution. Sounds like what's the probability of this many failures before my first success. Learning checkpoint. According to a representative from an automobile manufacturer, the company uses 3,000 lock and key combinations on its vehicles. Suppose that you find a key for one of these cars. Give the expected number of vehicles that you would have to check to find one that your key fits. What is the probability that your key fits the third vehicle you check? Give the probability that you would have to check at most 3 vehicles to find one that your key fits. This is actually more relevant nowadays when you have the touchpad security systems on cars. So you imagine how many different combinations you can have with, say, 3 digits that you need to key in, and all the different combinations, and then the security provided by that. So again, you have those solutions on the blackboard. Okay, I'm going to end this recording session for now, and we'll resume with the negative binomial distribution.